In Chapter 3, Part 6, Limiting Reactions, we're going to talk about probably one of the most dreaded topics in Gen Chem 1. So a limiting reactant, what is it? The limiting reactant is the object or the part of this reaction that limits the amount of product created. So when we start with unequal amounts of reactants, one of them determines how much product we're going to make. So if we go back to, I don't know, my most favorite equation right now, with a grilled cheese. So we know that there are two breads. Plus one cheese gives us one grilled cheese. So if you come to my house, let's just say I have a loaf of bread and I have 15 slices of bread. And we're going to open the cheese pack and there are 18 or just 8 slices of cheddar. So I want to know which of those is going to control how many sandwiches I'm going to make. So the trick is, how do we figure this out? So in your mind, you've probably pictured a sandwich and likely already identified which of those is the limiting reactant. And that's good. It tells me that you're going to be able to solve this equation for anything that is chemically related, because making grilled cheese can be something you can write an equation for. So the way I like to think about it is that we're going to take our 15 breads and we're going to figure out how many pieces of cheese we need. So 15 breads, and there are 2 breads for 1 cheese, and so that gives you 7.5 cheese. Okay. Well, if we have 8 cheese, we would need 1 cheese for every 2 breads, and so you would need 16 breads. Now, you and I are both somewhat aware that we're not really going to make half of a grilled cheese, but for the purposes of this example, we're going to roll with that. So one of these tells us that we need more than we actually have. So in this case, we need more bread than we have. Because over here, this is what we have, and this is what we need. So let's think about this top example. If we have 15 slices of bread, we need 7.5 slices of cheese. Well, we have 8 slices of cheese, so we are going to have enough cheese. If we want to use all of the cheese, we need 16 slices of bread. We're 1 slice of bread short. So in this case, what we want to say is that bread is our limiting reactant. And so the other thing that we're going to say is that means that cheese is the excess reagent. And so a lot of times we want to ask, well, how much is left over? So for the purposes of this, we're going to use all the bread. All of the bread is going to be used. So the excess reagent is how much cheese is left after we've used everything we have. So if we have 8 cheeses minus the 7.5 cheese that we're going to use, we're going to be left with half a slice of cheese. So a limiting reactant question feels like it's got to be really complicated, because we need to figure out how much did we have, how much do we need. So far, none of these calculations have asked or informed us how much product did we make. So how many sandwiches did we make? So the last thing we want to do is ask that question. So we're going to take our 15 slices of bread and we're going to convert that to grilled cheese sandwich. So there are 2 breads for every 1 grilled cheese sandwich. And so we're going to have gotten 7.5 grilled cheese sandwiches. So this is our product. This is how much we expect to get. So let's start with a kind of simple question. We're going to go back to our originals. We're going to start our 2H2 plus 1O2 gives us 2H2O. But now we're going to start the reaction with 10 moles of hydrogen gas and 7 moles of oxygen gas. Now, there are other ways that you can solve these problems. I'm showing you the way that I like to think about it. So the question asks, what is the limiting reactant and how much of the excess remains? So to do that, we're going to convert our, 10 moles of H2. We're going to convert that to the other reactant. So if there are 2 moles of H2 and 1 mole of O2, which means that we need to have 5 moles of O2. So in this case, we could stop right here. This will tell us what is our limiting reactant. But let's say you had chosen to work first with oxygen. So what do we do with that? So 7 moles of O2. There's 1 mole of O2 for every 2 moles of H2, which means that you need 14 moles of H2. So over here on the left, this is what we have, and this is what we need. So if you have 10 moles of O2, 10 moles of H2, you need 5 moles of hydrogen. So what we want to think about next is, well, how much oxygen gas do we have? We have 7 moles. So what this tells us is that the hydrogen gas is going to be the limiting reagent. So H2 is limiting. So the limiting reactant controls how much we use. So in this case, we're going to consume all of the hydrogen gas. So if we consume all of the hydrogen gas, we're going to use 5 moles of O2. This uses 5 moles of O2. So it also asks how much of the excess remains. So if we use 5 moles of O2, but we have 7, so 7 moles of O2 minus 5 moles of O2 tells us that there are going to be 2 moles of O2 remaining. So there are other ways that you can do these problems. I am always going to ask, and so is the homework, what is the limiting reactant and how much of the excess remains? So in our next example, we want to make LEDs. We're going to react molten gallium with arsenic to make gallium arsenide. And so we're going to have 4 grams of gallium to react with 5.5 grams of arsenic. What is the limiting reactant? How much of the excess is left? And how many grams of gallium arsenide is produced? 3 questions. So the thing is, before we do anything else, we actually need a balanced chemical equation. So we're going to have molten gallium, which is a liquid, plus arsenic, solid, gives us gallium arsenide, which is also a solid. So we have a balanced chemical equation. They are all in a 1:1:1 ratio. So in this case, now we need to figure out what we have and what we need. So it's going to become a much longer calculation than it was before. So in order to identify the first thing is the limiting reactant. So what are we going to do? So I'm going to convert my 4.00 grams of gallium to grams of arsenic. So there are 69.72 grams of gallium and 1 mole of gallium. And then we have 1 mole of gallium reacts with 1 mole of arsenic. And then 1 mole of arsenic has a mass of 74.92 grams of arsenic. So when we plug this into our calculator, we get 4.298 grams of arsenic. So this could be the end of the question. I am going to go ahead and I'm going to go ahead and solve if you had started with arsenic. So if you had started with arsenic, you're going to take your 5.5 grams of arsenic. We're going to do a very similar calculation, except there are 74.92 grams of arsenic and 1 mole of arsenic. And 1 mole of arsenic interacts with 1 mole of gallium. And 1 mole of gallium, that's 69.72 grams of gallium. And so that gets you 5.118 grams of gallium. So again, what we see on this side is what we have. And over here is what we would need. So when we look at this, to use up all 5.5 grams of arsenic, we need 5.11 grams of gallium. We only have 4 grams of gallium. Therefore, the 4.00 grams of gallium equals the limiting reactant. So gallium is going to be all used up. And so there will be none left. So the next part of the question asks, how much of the excess is left? So we need this much arsenic. But we started with 5.50 grams of arsenic. We're going to use the 4.30 because I used the sig figs here to round, which would have been 4.30 with sig figs. And that equals 1.20 grams of arsenic. Sorry, left over. So there's no gallium left, and there's 1.2 grams of arsenic left over. And the last thing the question asked is, how many grams of gallium arsenide is produced? Well, now we need to convert our 4.00 grams of gallium to gallium arsenide. So there are 69.72 grams of gallium and 1 mole of gallium. And there's 1 mole of gallium for every 1 mole of gallium arsenide. And 1 mole of gallium arsenide weighs a total of 144.64 grams. So when we plug this into our calculator, we will get that there are 8.30 grams of gallium arsenide. So there are 3 questions that we've answered in this problem. You can find those here. So in a question like this on an exam or on an assignment, you don't have to necessarily show all of this work. But this is the easiest, most straightforward way for you to get to the answer. In this example, our scientist is going to mix together 3.05 grams of titanium metal with 6 grams of chlorine gas to form liquid titanium 4 chloride. Then we want to know what is the limiting reactant, how much product will be formed, and how much of the excess reagent is left. You'll notice this doesn't have a balanced equation, so we're going to need to create that. So we have titanium solid plus chlorine gas. So don't forget, chlorine is a diatomic, comes as a pair. And so from here, we're going to make titanium 4 chloride, so that's Tl4, and that's going to be a liquid. So in order to balance this equation, we need to put a 2 right here, and so now all of our reagents are balanced. So now that we do this, we can go ahead and continue to solve this problem. So now we need to solve how many grams of chlorine will react with 3.05 grams of titanium metal. So we're going to take our 3.05 grams of titanium and convert that to chlorine gas. So there are 47.88 grams of titanium in 1 mole. And there's 1 mole of titanium for every 2 moles of Cl2. And 1 mole of Cl2 weighs 70.90 grams. So we would need to have 9.04 grams of Cl2 to use all of the titanium. We, in fact, only have 6 grams of chlorine gas, so we know that that's going to be the limiting reactant. So we're going to take our 6.00 grams of Cl2 gas. We're going to convert that to titanium. And so there are 70.90 grams of Cl2 in 1 mole of Cl2. There are 2 moles of Cl2 for every 1 mole of titanium. And 1 mole of titanium weighs 47.88 grams. And so that gives us 2.03 grams of titanium. So to use up all of the chlorine gas, which is our limiting reactant, they're going to need 2.03 grams of titanium. So chlorine gas is the limiting reagent. There are 0 grams left over. So the limiting reagent or the limiting reactant is all used up. So it asks how much titanium is left, and so we're going to take our 3.05 grams of titanium and subtract the 2.03 grams that we're going to have used, and that's going to give us 1.02 grams of titanium. So now this box right here answers 2 of the 3 questions. The last question is, how much product will be formed? So we're going to use our limiting reagent. So we're going to use the 6 grams of chlorine, or 6 grams of chlorine gas, and we're going to convert that to titanium 4 chloride. So we're going to take our 70.90 grams of Cl2, which are equal to 1 mole of Cl2. In the equation, 2 moles of Cl2 are required to make 1 mole of titanium 4 chloride. And so 1 mole of titanium 4 chloride is equal, or weighs 189.68 grams. So when we plug this into our calculator, we get that there are 8.03 grams of titanium 4 chloride created. And this is, in fact, the answer to the second question, or the second question. So chlorine gas is our limiting reagent, and there's 1.02 grams of titanium left over, and it makes 8.03 grams of titanium 4 chloride. So as we continue to think about reactions, we want to start to talk about yield. So how much do you get at the end? So in the previous problem, we talked about how much titanium 4 chloride is made. And so in this case, the theoretical is how much you expected to make. And so the actual is the amount that you collected. So let's go back and think about a grilled cheese sandwich reaction. So we're going to take our trusty equation of 2 bread, solid, plus 1 cheese, also solid, and that's going to give us 1 grilled cheese sandwich. And so in this case, we are going to use a slightly different amount than we started before. And so we're going to use 18 slices of bread because I got more at the store, but I only have 6 slices of cheese. And so when we think about this, we're going to look at it and think like, okay, what's the limiting reactant? How much did we expect to make? So we're going to take our 18 bread and convert that to cheese. So there's 2 breads for every 1 cheese. So 18 slices of bread requires 9 cheese. And so 6 slices of cheese, 1 cheese converts to 2 bread, and that means that we need 12 slices of bread. So that tells us that the cheese is the limiting reactant. And so if we were to use our limiting reactant of 6 slices of cheese converts to for 1 cheese to 1 grilled cheese sandwich, we could make up to 6 grilled cheese sandwiches. Now, I'm at my house by myself. I'm only going to eat 1 grilled cheese sandwich. So this is the theoretical. So the actual, in this case, it was only 1 grilled cheese sandwich. So the actual yield is what I actually made. So that means that we have leftover of both. Now, in terms of a chemical reaction, it's a little bit different because it's not like there would be excess reagents of both of our starting materials. Our starting materials or the reactants would be consumed, but maybe the reaction didn't work well. It didn't work well at all. And so in this case, once we know the actual yield, we can calculate something called the percent yield. So this is, in fact, kind of asking the question, like, how well did this work? And so the percent yield is the actual yield divided by the theoretical, multiplied by 100, and that gives you the percent yield. Oops. And so if we think about my grilled cheese sandwiches, I made 1 sandwich. I could have made up to 6. We're going to multiply that by 100, and that's going to give me my percent yield. And so 1 divided by 6 gets you 16.7% yield. So I made 16.7% of the possible. Now maybe I burnt the other 5 or something else, but the actual is what you actually collected. This comes from the lab. So the actual comes from the lab. The theoretical comes from math. You looked at what you started, your starting materials, and you calculated that. But your actual is what you actually got. So let's start to think about what that means. In this problem, where we have our scientist that's creating titanium 4 chloride, the scientists collected these 7.7 grams of titanium 4 chloride. So what is their percent yield? So to remind you, we're going to take our titanium solid plus 2 Cl2 gas, and that's going to give us titanium 4 chloride, which is a liquid. And so we're going to use our limiting reactant, which is the 6 grams of chlorine, to calculate the theoretical yield. So our 6 grams of chlorine gas converted with a 70.90 grams of chlorine gas in 1 mole of Cl2, there are 2 moles of Cl2 for every 1 mole of titanium 4 chloride. And so 1 mole of titanium 4 chloride weighs 189.68 grams. So in this case, this tells you that your theoretical yield is 8.03 grams. So this is our theoretical. So it's asking what is their percent yield. So percent yield is actual divided by theoretical times 100. So we're going to take the 7.70 grams divided by the 8.03 grams that they should have gotten. We're going to multiply that by 100. And then we're going to get 95.9% yield. So in this case, they got 95.9% of what they expected. So in this example, we have a balanced chemical equation. We have 2 moles of silver nitrate aqueous plus 1 mole of solid magnesium chloride is going to give us solid silver chloride plus aqueous magnesium nitrate. So it's fully balanced. And in this case, our scientist wants to make silver chloride from silver nitrate and magnesium chloride. The scientist mixes 12.34 grams of magnesium chloride into a silver nitrate solution. They collect 20.15 grams of silver chloride. What is the percent yield? And so in this case, it tells us that magnesium chloride, because it's the only thing we got, is the limiting reactant. So from here, we're going to take our 12.34 grams of magnesium chloride, MgCl2. We're going to convert that over to silver chloride, which is this one. So it's 95.12 grams of magnesium chloride in 1 mole of magnesium chloride. And so in the equation, there's 1 mole of magnesium chloride for 2 moles of silver chloride. And 1 mole of silver chloride weighs 143.22 grams. So when we plug this into our equation or into our calculator, we get 37.15 grams of silver chloride. So they should have gotten 35, but they only got 2015. So to calculate the percent yield, we're going to take our 2015 divided by 37.15, multiply that by 100, and that's going to give you 54.24%. So you'll notice that I'm continuing my use of significant figures. The problem, both of these values have 4 sig figs, and so that's how many your answer should hold. So in this example, where we have a balanced chemical equation, adipic acid, which is this chemical, is used to produce nylon, but we're going to make it from cyclohexane, which is this, and O2. So we're going to start the reaction with 25 grams of cyclohexane and 98.2 grams of oxygen. What is the theoretical yield? Now, it doesn't tell you to figure out what the limiting reactant is, but we need to know that because we have 2 starting materials and we need to know which one is the limiting reactant. So we're going to start with the cyclohexane. And so we're going to take our 25.0 grams of cyclohexane, C6H12, and we're going to convert that to oxygen. So 1 mole of cyclohexane is 84.18 grams, and 1 mole of C6H12. And based on our equation, there are 2 moles of C6H12 for every 5 moles of O2. And 1 mole of O2 is 32 grams of O2. So when we plug this into our calculator, we get 23.75 grams of O2 with sig figs, SF, that would be 23.8. So this information right here, once I can get it backed out enough, tells us that this is our limiting reactant. So it tells us that because we need less oxygen than we have. So we have 98 grams, we only need 23. So cyclohexane is the limiting reactant. So we don't have to do more calculations, we can just go from here. So we're going to take our 25.0 grams of C6H12. We're going to convert that to adipic acid. So there are 84.18 grams in 1 mole of C6H12. There are 2 moles of C6H12, and that creates 2 moles of H2C6H8O4. And 1 mole of H2C6H8O4 weighs 146.16 grams. When we plug this all into our calculator, we get 43.4 grams of adipic acid is our theoretical yield. C6H8O4. So we have a theoretical yield. Sorry. But we only obtained 33.5 grams. So what is the percent yield? So we're going to take our 33.5, we're going to divide that by 43.4, multiply by 100, and that's going to give us 77.2% yield.